In the previous lecture, we talked about this example and we couldn't finish it. Here, we talked about this example, which is about half range for a series. We were working to find the half range for a series for this example. In the example, as you see, we have given from 0 to 1. It's half of the range. It's not from -1 to 1. It's from 0 to 1. Okay, it's half of the range. So here we should find Fourier cosine series and Fourier sine series. For Fourier cosine series, we find this formula. In the formula here, we have a naught and an. We find a naught and an. Then you replace here, we get the solution for cosine series. But for sine series, for sine Fourier series, yeah, we finished this part, and now we have Fourier sine series. For Fourier sine, we find only Bn here. But before we do that, here to get Fourier series, Fourier sine series, for Fourier sine series, we say if the function is an odd function, we just need to find Fourier sine series. If the function is an odd function, we just need to find the sine Fourier series. Okay, here we need to extend f of x to be an odd function as shown below. Look, here we are going to show the other part, or we are going to extend the function f of x. Here we have given f of x, which is this function. This is the function. This function is given. Here, this is the function which is given. Now we are going to write down a piecewise function based on this function. This function is a part of the piecewise function. I write down the other part to be an odd function. To be an odd function. It's easy to find the other part from its graph. From its graph, we say the graph of an odd function, it is symmetry to the origin. It's symmetry to the origin. But for the even function, for the other part that we did before, this is the function which is given, and we found this red part. It's a symmetry to y-axis. If a function is an even function, it must be symmetry to y-axis. Okay, but here for finding, let's write down the function f of x is 1 minus x. F of x is 1 minus x. This is the given function. It's from 0 to 1. Sorry. 0, 1. Where x is from 0 to 1. That's given. Now we must find a piecewise function such that this function to be a part of the piecewise function, and we create the other part to be an odd function. Look, first we draw the graph for this function. We draw the graph for this function. So the graph of this function is the graph for this function f x is y equals 1 minus x. That's it. It's f of x. Okay, it's y equals 1 minus x. This is x and this is y. Yeah, let's say it's 1 and this is 1. We say if x to be 0, y is 1, and if y to be 0, x is 1. This is, look, we must take the graph, we must sketch the graph in this interval as from 0 to 1. X is from 0 to 1. As you see, this is the graph. This is the graph. This is the graph of 1 minus x. Yes. Now we are going to find the other part for this function. We say f of x equals, this part is given, which is 1 minus x, where x is from 0 to 1. Okay. Now we find the other part for the function. What's the other part for the function f x from -1 to 0? What's this function? Here. Now we draw the graph for that part. We say a function is an odd function if it is symmetry to the origin. That means we are going to find the symmetry for this part, for this graph here. Okay, look, this is the symmetrical part for that graph. Is it? It's symmetry to the origin. Let's use another color. Yeah, this is the graph of the symmetrical part of the graph. Now this point is 1 and this point is -1. Both are -1s. Okay, here we find the equation for this line. We find the equation for this line. We say if x to be 0, y is -1. Is it? This is 0 and -1. That's why you say if x to be 0, then y is -1. And if x to be -1, y is 0. Y is 0. Here we say y equals -x minus 1 is the function for this graph. Okay, look, if x to be 0, y is -1. Okay, and if y to be 0, if y to be 0, x is -1. Yes. بلا اخلي العكس كنا اما شلون عكس؟ It must be -x, -1. Look, if it is -1 plus x. Okay, in this case, if y should be 0, x is 1. That's why we cannot do this. Or we can say it is the graph of this function was shifted to 1 unit to down. This is -x. Okay, and if we shift this graph 1 unit to down, that means we subtract 1 from the function. That's -x. If we subtract 1, we get -x, -1. And for this part, it's the same graph, but we shift 1 unit to up. That means we add 1 for the function. It's -x plus 1, or 1 minus x. It's the same. Here, this is the graph for the function, or this is the function for the symmetrical part, which is -x minus 1. This is the function f of x. This is the extension of f of x, which is an odd function. Okay, now we find the Fourier sine series for f of x. We find the Fourier sine series for f of x. We say f of x is the sum of bn sine n pi x of L. This is the rule for finding the sine Fourier series. And here we should find bn. We should find bn. And bn equals 2 over L. The integration from 0 to L for f of x times sine n pi x of L dx. We find this integration. Here, f of x is given. F of x, let's first write down L. Here, L is 1. This is 1, as you see here. It's 1. So you get 2 integration from 0 to 1. For f of x, what's the function from 0 to 1? What's that part of the function from 0 to 1? It's this part, is it? It is from 0 to 1. As you see, the piecewise function, the function for the part from 0 to 1 is 1 minus x. So you just use that part. Okay, we just use that part. So we replace f of x in the integration by 1 minus x. We replace it by 1 minus x. Then we have sine n pi x L over L, L is 1, so you don't need to write down dx. Now we take this integration, we find this integration, and this integration could be done by, it's written down here. Let me write down here again. We say Bn equals 2 integration from 0 to 1 for 1 minus x sine n pi x dx. Okay, now we find this integration. We find this integration. This integration can be done by using integration by parts or UDV. Here we use short method for finding it. We say derivative to be 1 minus x and integration to be sine n pi x. Now we take the derivative for 1 minus x till we get 0. Yeah, it's -1. The first derivative is -1 and the second derivative is 0. So we just need to take two derivatives. So now we take 2 integrations for I. 2 integrations for I, it's sine. Integration of sine is negative cosine. Look, this is sine n pi x. It's the same as to say sine 3x. This 3 represents n pi. N pi is a constant, yeah. Here, the integration of sine n pi x is minus 1 over n pi cosine n pi x. Again, we take another integration. The integration of cosine is sine. It is minus 1 over n squared pi squared sine n pi x. Now we multiply these two, then negative sign multiplying these two. So that's the result for the integration. This equals to 2 times 1 minus x times -1 over n pi cosine n pi x. Then negative times negative is negative. It's positive. Times negative is negative. So you get negative minus we get minus 1 over n squared pi squared sine n pi x. It's all from 0 to 1. We now replace x by 1, then by 0. If we replace x by 1, this becomes 0, is it? Here we have 1 minus x. If we replace x by 1, this bracket becomes 0. Multiplying by that bracket is still 0. It's 2 times 0 minus. If we replace this by 0, we get sine n pi. Sine n pi is also 0. Sine n pi is 0. Yes. Which one? This one? Do you mean this should be positive? Look, it's integration. It's not derivative. Yeah. Derivative of sine is negative cosine. Sorry, integration of sine is negative cosine. But integration of cosine is sine without changing the sign. This is 0. And cosine n pi is, and sine n pi is 0. This is for the first value of x. As for x to be 1. Then minus. Replace x by 0. If you replace x by 0, here we get 1. The first bracket becomes 1 times minus 1 over n pi cosine n pi x. If we replace x by 0, we get cosine 0. Okay. Minus 1 over n squared pi squared sine 0. Sine 0 is 0. And this equals to 2 times. Here we get 1 times minus 1 is minus 1. And here we have this negative sign also, it becomes plus 1. Cosine 0 is 1. We get 1 over n pi. Okay? And here we have this negative sign. Multiplying by this negative sign becomes positive. But sine 0 is 0. So this all becomes 0. It's 1 over n pi. So the result is 1 over n pi. It's equals to 2 over n pi. This is Bn. So now we found Bn. We replace Bn here in this series, which become the sine Fourier series for the function. We say f of x over sine Fourier series for the function is the sum n from 1 to infinity for Bn, which is 2 over n pi, times sine n pi x over L. L is 1. And this equals to, here we just need to remove this. This is the solution for the cosine Fourier series for the function, for the given function. Okay. Here, for half range Fourier series, we should find sine Fourier series and cosine Fourier series separately. Okay. And that's all. And here you have a list of exercises. It's for yourselves. No, we have one more chapter. We start now. This chapter is the last chapter is about partial differential equations. Up to now, we talked about ordinary differential equations, but now we have partial differential equations. Here we talk about these topics in this chapter. The topics are here. The first section is about basic definitions and terminologies. Then in the second section, we have method of separation of variables. We use method of separation of variables through this chapter for solving the partial differential equations. We just use this method for solving the partial differential equations in this chapter. Then we have solving heat equation by using method of separation of variables. Then we have D'Alembert method. And then we have solving wave equation by using method of separation of variables. And the last one is solving Laplace equations by using method of separation of variables. We have these topics in this chapter. And in all, we use separation of variables for solving the partial differential equations. Here, each of these equations, when you say solve heat equation, wave equation, Laplace equation, these all are partial differential equations. We solve those partial differential equations by using a method of separation of variables. Up to here. For test 2, only chapters 3 and 4 are included. Yeah. Laplace transforms and Fourier series. Those 2 chapters are included for test 2. We now have some terminologies and definitions. We say we have partial differential equations. We say we let u to be u of xy. As you see here, we have 2 independent variables, which are x and y. But in the previous ones, we have only x or we have only t. Okay? But here we have 2 independent variables. We say a partial differential equation. A partial differential equation is an equation containing at least one partial derivative of u. If you have at least one partial derivative of u in the equation, we say that's a partial differential equation. Here, these are the partial derivatives of u. We say u sub x, which is partial u by partial x. And also, yeah, we now have another example. Here we have two exercises. I'm going to do one of them and the other one for yourselves. The first one, it says, reduce the following partial differential equation to two ordinary differential equations by separation of variables methods. Here we use the method of separation of variables to reduce this partial differential equation to make two ordinary differential equations. We do as we did before. We first, what we do, our dependent variable is u, and the independent variables are x and t. We say let u of x and t, we let u of x and t, which equals to x of x times t of t, be the solution of the partial differential equation. If u to be the solution, so it must satisfy the partial differential equation. In the partial differential equation, what are the partial derivatives in it? What are the partial derivatives in the partial differential equation? Here we have two partial derivatives with respect to x. Here we have the second partial derivative with respect to x, and also we have second partial derivative with respect to x. We now take the second partial derivative with respect to x for u, and also we take the second partial derivative for u with respect to t. That means here we find u sub tt. This is the partial. Let's first write down the partial differential equation. It's u sub tt equals alpha squared u sub x. It's u sub tt equals alpha squared u sub xx. Here we must find u sub xx and u sub tt. Then we replace them here in this partial differential equation. We say u sub tt equals to what? It's xt double prime, is it? Since u is x times t, so u sub tt is xt double prime, because in x we have no t, so it's a constant. We have t in only the function of t, and the derivative of t with respect to is t prime, and the second derivative is t double prime. This is u sub tt, and for u sub xx is x double prime t, is it? Here, this is our solution. This is u. To find the partial derivative for this function with respect to x, t of t is a constant. So we just take the derivative for x, was x prime, x double prime, x triple prime, and so on. Here we have two partial derivatives, so we get x double prime times t is for u sub xx, and for u sub tt we get t double prime times x. That's it. Now we substitute these. Let's name this to be 1 in 1. What we get if put this into the partial differential equation, we replace u sub tt by x t double prime. We get x t double prime equals alpha squared. We replace u sub xx by x double prime t. We replaced by x double prime t. We separate the variables. The variables with the derivatives together inside of the equality. So here we have x with t double prime. So we must remove this x here. And we also must remove this t here and this alpha squared also. How to remove these? To remove x in the left-hand side, we divide both sides by x. We divide both sides by x. And to remove alpha squared, we say alpha squared x. And to remove t, we divide by t. That means we divide both sides of the equality by alpha squared xt. And if we divide the left-hand side by alpha squared xt, we divide this by alpha squared xt. X and x are cancelled. We get only alpha squared t in the denominator. We get only alpha squared t in the denominator. We get t double prime dividing by alpha squared t, okay, equals to. Then, if we divide the right-hand side by alpha squared tx, t and t, alpha squared and alpha squared are cancelled, we get only x. And that t and also alpha squared in the numerator are going to cancel out. You get x double prime dividing by x. Here, we have these two equations. And these two equations are equal in only one case, if both are constants. So we equal this to lambda. We equal both to lambda. Now, we say the first part equals to lambda and the second part equals to lambda. We separate, equal both to lambda. For the first one, we say it's x double prime over alpha squared t equals lambda. And for this one, that's for this. And for that one, we say x double prime of x equals lambda. We now multiply this to the right-hand side. And we multiply this to the right-hand side. We get x double prime equals lambda alpha squared t. That's it. We just multiply both sides by alpha squared t. Okay. I'm جيري نائب يعني شلون جيري كني هم هبلا ضرب جيري كيكين لا راس ضرب جيري كني قاعد شيء alpha squared t. I'm بو أبي تريش يعني. Which one? Look, no. This is the wave equation. It's wave equation. It's wave equation. The partial differential equation is the wave equation. We reduce it to two ordinary differential equations. Yes. A functional wave. I can do ordinary differential equation. دواتر السباسين لكن دواتر باسي شلون do ordinary differential equation. شكارة كيت دواتر على شكارة wave equation. سيرجع هر ODE هو partial differential equation. إما كانوا ب ODE بلا do ODE معناه بيكو do ODE بيكو شكارة كنت هذا. Okay, and here for this one, what's in the right-hand side, we how to remove this x here? We multiply both sides by x. We get x double prime equals lambda x. And now we move this to the left, and we also move this to the left. We get, so this is t double prime. This is t double prime, not x, sorry. And here we say t double prime minus lambda alpha squared t equals 0. This is an ordinary differential equation. It's a second order ordinary differential equation. And also for this one, we get x double prime minus lambda x equals 0. It's also a second order ordinary differential equation. And differential equation second order that I do it. Okay. So that's how to use the separation of variables for reducing a partial differential equation to two ordinary differential equations. Yes.
So what's the role of alpha?
Alpha is a constant. It's a constant. It may be 4, it may be 10, any positive number.
So
it's a positive number. Yes, it could be changed. It's the constant of the wave. It could be 1. It could be 4. It could be 3. It could be 10.
I mean, for example,
Look, it's alpha squared. It represents that amount which here is always positive. لما يريدوا جاية فاتها هميشة موجبة. Why? It's okay. But here, look. If this with x if this with x. Okay, here, look what we get. No, it's okay. بابا بلا اسمه آسان تر جيب أنجا برام أبي تريان شيء تزكي سيرك ألفا سكوير إكس دبل برايم ناقص لامدا إكس يساوي بصفر أما تزكي ليه وايا بردمي إكس دبل برايم حتى سادة تربي آسان تر بوين بوش كردنا سري بردمي داتا شاو كان حتى سادة تربية أبي خويك بباشترين آسان ترين بوكيش بانجا اوكي كواتليرا هول بعمليرا نيل شو نيل هلا اول ودابا شوي كم بكره يقول لك سنه كذلك اشيت لايتي لقلتي تي برايمانيه اشيت اللي قلتي كعبه كشيء وماش انجام ده زي كشيء اوكي بالي but it's better to be with T. Yes. But okay, we now have this Laplace equation. How to reduce this to two ordinary differential equations? It's for yourselves. Okay, it is for yourselves. We now have solving heat equations. This is the heat equation, and these are the initial conditions. Here we have three types of heat equations, which are zero endpoints. If the conditions are like this, look, the boundary conditions decide on the type of the wave equation. It's zero endpoints. It's zero endpoints, and insulated endpoints, which you have condition like this. If the condition is on this form, it is mixed endpoints. Okay, if the conditions, if none of them are derivatives, here we have u of 0 and t and u of l and t. It is zero endpoints. But if we have u sub x and u sub x of x and 0 and l and t, here we have both are derivatives with respect to x. This is called insulated endpoints. And if we have both u of x0 and u sub x of l and t, if you have both, we say it is mixed endpoints. Yes. بفي condition الشواذ يحلك شي جوازه. Okay. Yes. Yes, of course. Here we have an example. It takes a long time because here it leaves 4 pages for the solution. Only one example, okay? We solve it tomorrow. Okay. Sorry. Yes, we do it tomorrow. Okay. So it's enough for today.